Okay, in this video, we're going to talk about continuity. A continuous function is a function that has no breaks in its graph, and within its domain, there are no x values that have to be excluded. Now, it's often more helpful to talk about what discontinuities are to help us understand more as to how to define continuity itself. We have three types of discontinuities. You have a hole, which is basically a single blip in a graph that had to be removed. However, the function itself from left and right sides will have a limit that exists around that hole. You also have, and that's a removable discontinuity. You also have two non-removable kinds of discontinuities. You have vertical asymptote, which means the graph will show unbounded behavior at that x value, and have a non-removable discontinuity of a jump, which basically the function is continuous everywhere, but at that x value, you have a gap in two different y values, so where the limit does not exist. So to define continuity, we're going to look at a way to define continuity at a single point. And if I'm looking at a point x equals c, if the limit exists, so the limit as x approaches c for the function, and that equals what the function is defined at for that x value, it'll be continuous at the point. Now, another way to think about it is if the limit from the left equals the limit from the right and equals the function's value, it will be continuous at that point. So let's look at a graph here and work on our definition of continuity. So here we want to find the intervals where the function is continuous, identify the points of discontinuity within the interval, and figure out what part of the definition of continuity is missing. Well, if I'm looking at the graph and we're going from 0 to 5, the function itself is going to be continuous at everywhere where it doesn't have a break in it. So let's find our discontinuities. We have a discontinuity at x equals 1 because I have a hole. We have a discontinuity at x equals 2. We have a vertical asymptote. And we have a discontinuity at x equals 4. We have a jump. Now, we're going to use our actual definition of continuity with limits to figure out what part of that definition failed. And so we'll look at these kind of one at a time here. So x equals 1, x equals 2, and x equals 4. So we have a whole discontinuity. So what we have here is the limit as x approaches 1. Now, the limit exists because both the left and the right-hand sides equal each other. And in fact, the limit itself equals 1. So the limit as x approaches 1 is equal to 1. And the function is defined at 1 at a y value of 3. So f of 1 is equal to 3. So the reason why it is not continuous is because the limit as x approaches 1 for f of x is not equal to f of 3. So therefore, not continuous. So at x equals 2, we have a vertical asymptote. The left and the right sides are showing unbounded behavior. Now, I don't necessarily need the limits because in order to be continuous, the function has to be defined at that x value as a starting point. So I could say f of 2 is not defined so therefore not continuous. And lastly, we have the jump discontinuity at x equals 4. Now I look and I see, unlike at x equals 2, the function is defined here at 4. In fact, it's defined as having a value of 1. So f of 4 is equal to 1. So it met one part of the requirements in order to be continuous. However, the part that fails is the fact that the limit doesn't exist because the limit as x approaches 4 from the left does not equal the limit as x approaches 4 from the right, so therefore the overall two-sided limit can't exist. So the limit as x approaches 4 for f of x does not exist, and because of that, it's not continuous. So that's how we would use the definition of continuity to prove that a function is not continuous at a point. Now, let's say I had to accomplish the same goal, but I did not have a graph to do it at. So if I want to determine whether or not the function is continuous or not, I would just simply need to find the discontinuities. So look here at the problem up here on the top left-hand corner, and I figure out the value of x that makes the denominator 0, and that's going to be at x equals -1. Now to figure out the kind of discontinuity, I would need to fully factor the problem and see what happens. So I can factor that numerator factors to x minus 1 times x plus 1, and the denominator stays x plus 1. The fact that I can cancel out the two x plus 1s means that that discontinuity of x equals -1 is a whole. And then in my head, I know what part of the definition failed for continuity at x equals -1. If it's a whole, the limit would exist. However, the function is not defined there. So here I look at the second one, and I see that -2 makes the denominator 0, so I have a discontinuity at x equals -2. Now, the kind of discontinuity we would have here is if you look at the problem that you have, and we have x plus 2 over 2 plus x. So they are two factors that could almost be canceled out. However, the absolute value makes that part you'd have to be very careful of. So regardless of the number I put in for x, I'm going to have the same value in the numerator and the denominator. Just the numerator is always going to be positive, and the denominator has a chance to be the same number but negative, which means that if x is greater than -2, then f of x is going to equal +1. If x is less than -2, f of x will be -1. Discontinuity we would have would be a jump discontinuity. All right, look here at the third one. So find our discontinuities. Let's factor it. So the numerator would be 2 times x minus 1. The denominator is going to be x plus 2 times x minus 1. So we have more than one kind of discontinuity right here. So we have a discontinuity at two places. We have a discontinuity at x equals -2, and we have a discontinuity at x is equal to 1. The kinds of discontinuities we have a vertical asymptote at -2, and we have a whole at +1. The function is not continuous at these discontinuities because nowhere else in the problem do you have defined function values for these x's where the function is undefined. And also for the jumps and the vertical asymptotes, the limits don't exist, so therefore I can't be continuous. Now let's look at some piecewise functions here. Now, piecewise defined functions, you have to tread through these problems very carefully using your definition of continuity. And remember how or what the requirements are for a function to be continuous. When you do these problems, you typically look at the breaking points. And so I'm looking here first at the function x squared minus 1 over x minus 1. And I have this break here at 1 where I have to change functions. And I also look and I know that the function is defined at 1. So that f of 1 is defined in equals 3. So I did meet a requirement for the function to be defined there. Now the second part that we're going to do is we have to look and see what the limits are. What do the limits equal? So I'm going to find the limit as x approaches 1 from the left, because I got to do this twice. So the limit is x approaches 1 from the left for x squared minus 1 over x minus 1. Well, I could factor that, So the limit as x approaches 1 from the left, that's going to make x plus 1 times x minus 1 over x minus 1. The x minus 1s will cancel. The limit as x approaches 1 from the left, in this case I could use x plus 1. And then if I put in 1 from here, I don't put a number smaller one, you put 1 in here and you get 2. So the left-hand sided limit equals 2, and the right side limit, so the limit as x approaches 1 from the right, I would use x plus 3. I don't have to do any simplifying there. Put 1 in, and I get 4. So I look, it fails multiple ways. 1, none of those limits equal what the function is defined at, but 2, those don't equal each other. So the limit doesn't exist. So therefore, not continuous at x equals 1. Now let's look here at this next one. So this one we don't quite have so many parts in it. So as long as x does not equal 2, we're going to use that rational function. But when x does equal 2, we equal 3. So we do have a defined value for f when x is 2. So f of 2 is equal to 3. So that's the first requirement for continuity. The function needs to be defined at the x value. Now we start working for the next part of the definition. I need to evaluate the limit. Well, since we are going to be in that same equation the whole time, I can evaluate the two-sided limit. So the limit as x approaches 2. So this eliminated x value, I have to use a different equation or a different value in this place, in this case a point, for x squared minus 4 over x minus 2. We evaluate this limit by factoring. We can cancel out the x minus 2s. So this is going to leave me with x plus 2. And now we can substitute in, and we see that when we put 2 in, we get 4. So the limit existed, and the function was defined. However, it's not continuous. It's not continuous because the limit as x approached 2 for f of x did not equal what the function was defined at for 2. So it's important for these problems we figure out if it's continuous or not, and we give our reasoning for why it does not, or why it is not continuous at that x value. Okay, another example. So I'm looking, I have two linear parts. Linear functions are continuous for all real numbers on their domain. However, I have the breaking point here at 1. And so I need to check first that I am defined at the breaking point. And because of that inequality sign less than or equal to 1, I know that f of 1 is defined. F of 1 is going to be defined at whatever I get when I put in 1 for x right there. So I put 1 in for x there and I get 2. So f of 1 is 2. Now I proceed to find the limit as x approaches 1. And because I have two different functions at 1, I'm going to have to evaluate the left side and the right side limit in order to figure out what the two-sided limit is. So the left-sided limit, I would use the function of 4x minus 2, and I could plug 1 in immediately, and I would get an answer of 2. So the left-sided limit is 2. The right-sided limit, so the limit as x approaches 1 from the right, we use 5 minus 3x. I put 1 in there, and I also get 2. So the limit as x approaches 1 from both sides for this function is equal to 2. Notice that that also equals f of 1. Therefore, it is continuous. So f of x is continuous. All right, here in these next two examples, we want to use the definition of continuity to find the value of some constants, in this case a or b or both a and b, to make the function continuous. So here in this first problem, we are trying to figure out what does a need to be to make g continuous at x equals a. Well, what we do know is f of a is defined as equal to 8. So I do have a defined y value. So I would approach this problem by figuring out the limit. So the limit as x approaches a, we'd be using the top equation here of x squared minus a squared over x minus a. In order to be continuous, the limit as x approaches a for g of x, and actually I used the wrong letter here at the very beginning, that should be g of a, that needs to equal g of a. Well, we know that g of a was 8, so that means I need to set this limit equal to 8 to help me solve. Well, to do this, I'd have to factor the inside of the limit. So the limit as x approaches a, that'd be x minus a times x plus a over x minus a. It's equal to 8. Now I can cancel out these two parts here, and I get the limit as x approaches a for x plus a is equal to 8. Now what I would do is, just as if I was evaluating the limit as x approached a number, I'm going to take what x is approaching, I'm going to put it in for x. So that's going to give me 2a is equal to 8. And then divide by 2, and I get a to be 4. Now let's go to this next one. So we got 3 separate parts here to force the function to be continuous. In order for it to be continuous over its entire domain, it's going to have to be continuous at all these breaks. So at x equals -1 and at x equals 3. So I need to start working through my definition of continuity, and we'll start by, is it defined at the breaks? So f of -1 is defined, it equals 2. I'm going to do the same thing for 3. So at x equals 3, it's defined as equaling -b. So it will have values at the breaks. Now I have to look at finding the limits. So the second part is, even though it's defined, I need the limit to exist. So the limit as x approaches -1. Now we have breaks here, so I need to do from the left side. Now the left side of the limit is the limit of 2, which that one is going to equal 2. And the limit as x approaches -1 from the right for f of x, I would use the ax plus b, and that, in order for it to be continuous, the limit has to exist. So I would have to set it equal to the limit and what it's defined as, which is they're both 2, so I'm going to set it equal to 2. And now I'm going to work to solve. Well, I would now need to take that -1 and put it in for x, so that way I can get an expression. So that would give me -a plus b is equal to 2. So I have an algebra expression that I'm probably going to turn right around and get ready to use here in just a minute. Now I go to my second part where the break was, which was at x is equal to 3, and I take the same approach. So I know that f of 3 is defined as equaling -b. So now I'm going to look at the one-sided limit. So the limit as x approaches 3 from the left, and I would use the ax plus b equation. And I'm going to go ahead and put -3 in. Actually, in order to do that, that limit has to equal what it's defined as being -b. And so I'm going to set that equal to -b, and I'm going to put 3 in for the x, which is going to give me 3a plus b is equal to -b. Now, I don't necessarily need to do the right-sided limit, because the right-sided limit, if I were to continue, is going to be, as the limit as x approaches 3 from the right, I would use -b, and that I'm saying that has to equal -b, which is not going to allow me to solve for anything because I end up with a true statement, and so that's not going to necessarily help me. So I'm going to be working from this line right here. Now I could clean that line up and combine my like terms, and that would give me 3 times a is equal to 2b. So I have two expressions here. What I would do now is solve the system. So that way you can get values for A and B. So I'm going to take one of these equations, rewrite as a variable equals. I'm going to take this one, rewrite it as B equals. So B equals 2 plus A. And then I'm going to plug it into the other one. So I have 3 times A equals 2 times 2 plus A. So 3A is equal to 4 plus 2A. I subtract, and I get A is equal to 4. Now that I know A is equal to 4, I'm going to put that back in right here. And I get B equals 2 plus 4. And I get B is equal to 6. So I can make this function of x be continuous on its entire domain, even with the breaking parts at -1 for x and 3 for x, if I have a to equal 4 and b to equal 6.